Hello everyone, welcome to my curiosity project on amphibian land invasion and lung development for vertebrate zoology BIO-3040. Introduction. The conquering of land by amphibious tetrapods was crucial for the evolution of all modern land animals and vertebrates. Various adaptations were required to transition from the water to the land. One of the most important adaptations was the ability to breathe in air rather than breathe underwater with gills. Amphibians were successful in combining cutaneous respiration along with pulmonary respiration. This development of pulmonary respiration is what paved the way for lungs in reptiles and mammals and also gave us the ability to breathe in air. So, who are the amphibians? I want to start off by going through the amphibians and explaining who they are before we get into the details of how they evolved lungs. So the first tetrapods were amphibious and evolved into all vertebrates on land today. Modern extant amphibians are divided into three groups. These groups, as you can see in the table, are the Anura, which are the frogs and toads, the Chordata, salamanders, and Gymnophiona, caecilians. Sorry if I pronounced that incorrectly. Amphibian characteristics for life on land. So breathing in the air was not the only challenge in the move from life to land. There were several others as well, and I will mention them here. So it's believed that the amphibian ancestors arose from the lobe-finned fish, or the Sarcopterygi. And if you look at the figure on the right, it's very useful. The Sarcopterygi can be seen there breaking into the lobe-finned fish and the tetrapoda, which then break into the amphibians and amniota. Then the mammals and reptiles are branched off the amniota. But if you notice, it branches off to the amphibians first. So this shows that they are the oldest land vertebrates, older than the mammals and reptiles. So the limbs of land vertebrates come from the lobe fins of the Sarcopterygi, and these are essential for movement and the elevation to allow ourselves to breathe. Prevention of desiccation was also very essential when we first moved to land, because air is much drier than water. So early tetrapods possessed scales which stop water loss, but natural selection in amphibians gave way to the modern skin, which is permeable to moisture. This allows amphibians to stay hydrated and not desiccate. And as we've already been talking about, we will be talking about more later on, the respiration of air was needed, and this was possible through lungs and the skin respiration for the amphibians. Amphibian respiration and the role of lungs. So amphibian lungs are not as efficient or as good as higher mammals' lungs. They are more primitive and less specialized. So amphibians lack a diaphragm, which is the muscle that contracts for us to breathe, and other higher mammals. And their breathing is not constant, it's episodic, so it's only used sometimes. So the amphibian breath is more of a gulp than a reflex. It is an autonomic reflex for us, which can be controlled though, but anyway, it's not like that in the amphibians. And because of this, they also use cutaneous respiration through the skin because they need to. The lungs are not nearly as important in the amphibians compared to mammals. This would have been the same in the early development of the lungs, so in the early tetrapods. And there's a table there showing the different qualities of all the different vertebrates. And you can see for the amphibians that the breathing is with simple lungs and they have moist skin. The conflicting theories of lung development. So from this point on in the presentation, we'll be focusing on the evolution of lungs in amphibians and how it was possible and these theories that people argue about. So certain scientific sources theorize that lungs develop from the digestive tract. So this would mean the animal swallows air into the gut, and that's where oxygen is absorbed from, and eventually this would transform into lungs. And other sources claim that tetrapod lungs are co-opted swim bladders evolved for gas exchange rather than buoyancy control. And I will explain both of these theories, and they're both pretty interesting. Digestive tract theory. So this is the first of the two theories I'll explain, and in human embryo development, the lungs first appear as invaginations of the developing gut. So this is pretty interesting. This digestive tract theory claims that amphibious tetrapods exited the water to roam land before the formation of the lungs. And they did this by simply gulping air into their digestive system and absorbing the oxygen. So eventually, natural selection favored the formation of air pockets, or these invaginations of the gut, for gas exchange. These air pockets would have allowed early amphibians to exit the water for longer periods of time. So this theory states that lungs developed after we took over the land, and when we were first on land, we were just swallowing air into our gut and absorbing it. Slide number 2 of the digestive tract theory. So why did we even want to leave the water to live on land? And scientists claim that the reason for exiting the water to live on land is thought to be due to low oxygen levels in the ocean 350 to 400 million years ago. That is a long time. Today, oxygen concentrations are much higher in the atmosphere than the water. Air is approximately 21% oxygen, while less than 1% of water is composed of oxygen. So you can imagine that back then, things would have been somewhat similar, even though oxygen concentrations in the atmosphere changed over time. We would assume the same difference between the air and the water. So in the graph on the right, you can see the past billion years of atmospheric oxygen. I have no idea how they figured this out, but that's pretty cool. And we can notice that 400 to 300 million years ago, there was a huge boom in oxygen. So this is the time period that we're focusing on. Swim bladder theory. So this is number 2 of the theories that we'll be going through for evolution of the lungs. So scientists who advocate for this theory agree on a time period of 350 to 400 million years ago, when tetrapods began to invade land, and some fish already contained swim bladders. So these scientists theorize that as the need for atmospheric oxygen increased, natural selection caused the swim bladders to begin carrying a gas exchange, along with the buoyancy role. This variety of lung evolution is believed to be how lungfish developed lungs. But many fossils of early tetrapods seem to be missing lung structures, supporting digestive tract theory. So some people believe that the lungfish and swim bladder theory developed independently of tetrapods. On the right, you can see the anatomy of the fish. It's giving me flashbacks to lab, but we can see the large swim bladder, and we can easily imagine how that would start performing gas exchange for air if oxygen in the water was low. The more likely theory. So as I kind of foreshadowed on the last slide, the more popular and more likely theory is the first theory, the digestive tract theory, and it's more popular among scientists. So since fossils of early tetrapods lacked lungs, it is believed that the lungs evolved as invaginations of the digestive tract after we invaded land. I also personally think it is important to recall how lungs develop in human embryos, because we see that the lungs form from the gut. This is indicative. Final thoughts on this curiosity project. Genetic mutation and natural selection are responsible for the amphibian development of lungs and other adaptations for life on land, and all evolution in general in all animals. So I commonly think of evolution incorrectly and confuse behavioral changes as the driving force of evolution. This, of course, is incorrect, and random changes in the genome are the driving force of new behaviors in evolution. If these new behaviors are favorable for survival, then they will be naturally selected for, and the genome will carry on in future generations and give them these same behaviors and aspects. So the photo on the right is of the famous scientist Charles Darwin, and he was smart enough to figure all this stuff out, so props to him. Thank you for watching my curiosity project. It's much appreciated, and here's my references. There's 2 pages.